Today I'm going to run through the answers of the 7.7 worksheet. After I run through the answers, I will run through each problem individually, but you can fast forward just to see the problems that you need to see. And it might take a few videos because some of these are a little bit longer. So the answer to number 1, you should have gotten a concentration of Cl2 of 0.0625 molar. For 2a, our equilibrium constant expression should be the pressure of H2 squared times the pressure of O2 divided by the pressure of H2O squared. For part B, the pressure of O2 is 6.7 times 10 to the negative 6 atmospheres. The pressure of H2 is 1.3 times 10 to the negative 5 atmospheres. The pressure of H2O is 1.27 atmospheres. For 3A, the expression is the pressure of NO squared divided by the pressure of N2 times the pressure of O2. For part B, the pressure of N2 is 0.675 atmospheres. Pressure of O2 is 0.472 atmospheres. The pressure of NO is 3.91 times 10 to the negative 16 atmospheres. For number 4, the expression is the concentration of H2 times the concentration of Cl2 divided by the concentration of HCl squared. Part B, the concentration of H2 is 6.7 times 10 to the negative 18 molar. Concentration of Cl2 is 6.7 times 10 to the negative 18 molar. And the concentration of HCl is 0.375 molar. For 5A, we show the pressure of NH3 squared divided by the pressure of N2 times the pressure of H2 cubed. Part B, the pressure of N2 is 1 atmosphere. The pressure of H2 is 1.4 atmospheres. And the pressure of NH3 is 1.1 times 10 to the negative 2 atmospheres. For number 6, part A, it's about 0.093 molar. For part B, the concentration of PCl3 and the concentration of Cl2 are both equal to 0.067 molar. For part C, we had to draw on the graph. So originally on the graph, they give you this, PCl5. Remember the concentration of both reactants towards the end, they have the same stoichiometric coefficients and they're both starting at 0. So it would be something like this. Concentration of PCl3 equals concentration of Cl2. And at equilibrium, that value there should be 0.067. Okay, so that was part 6C. For part D, we should have gotten a value equal to 0.048. For 7A, our expression is the concentration of SO2 times the concentration of Cl2 divided by the concentration of SO2-Cl2. For part B, concentration of SO2-Cl2 is equal to 0.237 molar. And the concentrations of SO2 and Cl2 are both 0.306. For part C, our equilibrium constant is equal to 0.395. And for number 8, we have X, which is the pressure of N2, equal to 0.326 atmospheres. And for 9, we have 4X, which is equal to the pressure of NO, as 0.523 atmospheres. So now I'll run through each of these problems and go through the answers with you. Okay. So for number 1, it says the equilibrium constant is 0.1 at 25 Celsius. Find the equilibrium concentration of chlorine gas if the equilibrium concentration of ICl and I2 are known to be 0.5 and 0.4 respectively. So the first thing I do is I write out the equilibrium expression so that I know what's going where. And remember, it's products over reactants. So I have the concentration of Cl2 times the concentration of I2 divided by the concentration of Cli squared. They gave me the Kc of 0.1. And I know the concentration of I2 is equal to 0.4, and the concentration of CLI is 0.5, and don't forget to square that on the bottom. And I'm really looking for the concentration of Cl2. So if I multiply 0.1 by 0.5 squared, then divide by 0.4, you should get a value of 0.625 molar. So that is number 1. For number 2, part A, we're first solving for a Kp, so pressure, and it's the same idea, products over reactants. So I have the pressure of H2 with a coefficient of 2, so that's squared, times the pressure of O2 divided by the pressure of H2O squared. And remember to use rounded brackets for pressure always. We only use square brackets for concentration. So that is part A. For part B, I'm setting up basically an ice table here. So I have my reaction 2H2O yielding 2H2 plus O2. For my initial concentration, I have 1.27 atmospheres, 0 atmospheres, and 0 atmospheres. For the change, I have minus 2x, plus 2x, and plus x. And at equilibrium, I should have 1.27 minus 2x, 2x, and x. So if I were to plug in my values from up top here, they give me a Kp value of 7.6 times 10 to the negative 16, which is very small. So that means we can do a shortcut. We don't have to do a quadratic formula. Equals 2x squared times x divided by 1.27 squared. So I ignore that 2x because I know I have a very small value for my Kp here. If I go ahead and solve for x, I get x equals 6.7 times 10 to the negative 6 atmospheres. Okay. Due to sig figs, my final pressure ratio is the same as my initial, so it's just 1.27. Technically, you do subtract this, but again, due to sig figs, you're only reporting to 2 decimal places, so it rounds to the number that you started with. For H2, I have to multiply this value by 2, and for O2, it's just equal to this value here. Number 3 is very similar to number 2. We again have to find the equilibrium constant expression. So that is the pressure of NO squared divided by the pressure of N2 times the pressure of O2. Again, be sure you're using rounded brackets for that expression. For part B, I'm again setting up an ice table. So I have my equation N2 plus O2 yields 2NO. For my initial pressure, I have 0.675 atmospheres for N2. Put a line there so you know. And then 0.472 for O2. And I have 0 pressure for NO. For my change, it's going to be minus x, and plus 2x. At equilibrium, for N2, I should have 0.675 minus x. I should have 0.472 minus x for O2, and I should have plus 2x for NO. So again, if I plug and chug, I've been given a K value of 4.8 times 10 to the negative 31 equals 2x squared divided by 0.675 times 0.472. Okay, so again, I have a very small K value. That means that reactants are strongly, reactants are strongly favored because this is a smaller value. So there's not going to be much change in there, so I can go ahead and ignore those 2 x's in the denominator. So if I find and solve for x, I get x equals 1.96 times 10 to the negative 16 atmospheres. For N2 and O2, for sig figs, the pressures are going to stay the same. They're not going to change much, basically. And for NO, I multiply x, 1.96 times 10 to the negative 16, by 2. And I get 3.91 times 10 to the negative 16. Okay. Number 4, again, very similar, but this time we're dealing with concentration instead of pressure. I have a Kc value of concentration of H2 times concentration of Cl2 divided by concentration of HCl squared. Okay, so again, it's products over reactants, and then always raise their stoichiometric coefficient power. For part B, we're setting up an ice table. 2HCl going to H2 plus Cl2. ICE. I have 0.375 molar for HCl and 0 to begin with for H2 and Cl2. For change, I have minus 2x, plus x, and plus x. And at equilibrium, I'm going to have 0.375 minus 2x. I'm going to have x and x. So if I go ahead and plug in those values, the Kc value I was given is 3.2 times 10 to the negative 34. Again, small, so I can go ahead and ignore these, the x's in the reactant side, since reactants are strongly favored anyway. I have x times x, it's really x squared, divided by 0.375 squared. If I solve for x, I get a value of 6.7 times 10 to the negative 18 molar. Due to sig figs, concentration of HCl is basically the same. The concentration of H2 and Cl2 will both be equal to this value that we just solved for. And that's a very, very, very low concentration. Number 5, we're going back to a pressure equilibrium constant. So we have Kp is equal to the pressure of NH3 squared divided by the pressure of N2 times the pressure of H2 cubed. Okay, again, stoichiometric coefficients go to the power, and remember to use rounded brackets. Part B, we're again setting up an ice table. That's HCl. Sorry, wrong column there. We have N2 plus 3H2 yielding 2NH3. For initial concentrations, we are given, or initial pressures rather, we're given 1 atmosphere, 1.4 atmospheres, and 0, because initially we have no, looks like a 6, because initially we have no products. For our change, we have minus x, minus 3x, and plus 2x. So here we have 1 minus x, 1.4 minus x, and 2x. So we go ahead and plug in our values. We have 4.51 times 10 to the negative 5. Not much smaller than 1 times 10 to the negative 4, but still smaller. So we can go ahead and ignore those x's that come in the denominator. We have equals 2x squared. Be sure you square the entire thing and don't do 2x squared, because remember we have to distribute that square to both the 2 and the x, divided by 1 times 1.4. Okay, again, that's less than 1 times 10 to the negative 4, so I'm ignoring those 2 x's there. When I solve for x, I get x equals 0.006 atmospheres. My initial pressures for N2 and H2 are the same at equilibrium, so 1 and 1.4. If I do 2 times this value, I can find the concentration, or sorry, the pressure again, of NH2.